Good evening, and welcome to the Arthur C. Clarke Center for Human Imagination, located here in Atkinson Hall, the home of Qualcomm Institute, which is a part of the California Institute of Information Technology and Telecommunication. And there'll be a test on that when you leave, so remember that. I'm Sheldon Brown, the director of the Clarke Center, and you know, this is another in our continuing series of how we get smart people to talk about big ideas. And so tonight we have really an incredible opportunity to have a conversation with Freeman Dyson, and probably many of you know a bit about Freeman Dyson, which is why you're here. And I was mentioning earlier, if I gave these three people the full introductions they all deserved, that's about all the time we would have for tonight. But I'll give cursory introductions to them. And as people probably know, Freeman Dyson was a longtime professor of physics at the Institute for Advanced Study in Princeton, what he's emeritus with now. And like our namesake, Arthur C. Clarke, he was born in England, and they both were involved with the RAF in World War II. He graduated from Cambridge in 1945 in mathematics before he went on to study at Cornell as a graduate student working with Richard Feynman, among others, and has made major contributions in fundamental physics theory by uniting different versions of quantum electrodynamics. And over his years, his scientific work ranged across a lot of different fields, all with mathematics as this kind of underlying engine that has this application to all types of human endeavor. But ranging from nuclear physics and solid-state physics and astrophysics and biology. Had spent a great deal of time and effort in his career working particularly with nuclear physics and nuclear reactions and how they might be able to be applied to such audacious things as space travel. But then how they also get applied to more terrestrial uses, such as the development of isotopes for hospitals and university research. And his ideas have also given rise to some very, you think about his interest in developing nuclear technology for spaceships, and he thinks very, very broadly and large about things, such as how you might capture the energy of a sun. And his conception and invention of the Dyson Sphere, building off of ideas that actually kind of had were incubated in the science fiction of Olaf Stapleton. And then he furthers their development to this Dyson Sphere that ends up becoming a reoccurring trope in science fiction once again. So I've always found that cycle of ideas between science and science fiction quite interesting. And he's written more than a dozen books that demonstrate his imaginative and nuanced thinking about science and science's expanded relationship to other types of human thought, such as disturbing the universe, weapons and hope, infinite in all directions, the sun, the genome, the internet, and the dreams of Earth and the sky. And I always find it wonderful when I open the New York Review of Books and find a substantial review from Freeman Dyson. It's always one of the highlights of the year in the New York Review of Books. Now, he's won many awards that, just some examples: the Lorentz Medal, the Max Planck Medal, the Robert Oppenheimer Memorial Prize, and probably most importantly, the Arthur C. Clarke Lifetime Achievement Award. And he's also a longtime member of this, what is referred to as a semi-secret group, the Jasons. And I guess it's semi-secret because we know he's a part of it, but we barely know what they do, except come up with ways in which we hope they're actually helping keep us safe and sane and moving forward as a civilization. So thank you for that. And in conversation with Freeman tonight, to talk about these kind of myriad ways in which he thinks about things and has applied his curiosities over the years, we have two terrific people that are part of the Clarke Center. One is David Brin, who's the writer in residence of the Clarke Center, and is also a card-carrying physicist, having gotten his PhD here in astrophysics. And he's written over a dozen science fiction novels, along with many short story collections, graphic novels, and is often known for his novel *The Postman*, which was adapted into a movie by Kevin Costner in 1997. And David is also a consultant to numerous activities that are trying to keep our civilization safe and sane, or maybe a little cracked once in a while. And along with David, we have another card-carrying physicist, Adam Burgasser. And I will say that Adam is coming to the stage at the in place of Brian Keating, who about 30 hours ago or so became a new father, and so. But fortunately, we have a deep bench in physics, and so Adam's a professor of astrophysics here, and directs the Cool Star Lab. So if you want to go hang out with the hip stars, Adam knows where the cool stars are, and in an interesting way, kind of studies almost the opposite part of cosmology from Brian Keating, which is the kind of nearer, cooler parts of the cosmos. But Adam's work is also quite interesting. I think from the three of them, what we have are Adam does work that also intersects the arts in many ways, a number of collaborations on artistic projects, and very involved in physics education outreach. So I think from the three of them, we have united by physics, and then how physics can help diversify how we reimagine the world. So we look forward to the next hour or so about reimagining our realities, that these three are going to take us down that road. So,
thank you, Sheldon. Thank you, Sheldon. Let's make sure we can all be heard. Freeman, say something.
Am I heard?
Yes. We are very fortunate to live in a civilization in which wild and unconstrained minds like Freeman have been heard for a very long time and have helped to divert us from highly constrained paths. One of the things that I'm most keenly aware of as a science fiction author is not so much the influence of physics on what we write as history. And Freeman is not just living history, he's living evidence that our civilization is very different than it used to be. Much more willing to listen to wild minds. And I'd like to start, Freeman, by going back to, your childhood, a couple of formative things. You grew up in the Blitz, right in the middle of...
No, not really. I mean, I was already a teenager by then.
Well, then I'll go back to when you were a child, and I'll talk about whether or not you wanted to write science fiction back then.
Yeah, well, I did. I started a novel when I was 8 years old, which, of course, didn't get very far. But it had as its subject a collision between the asteroid Eros and the moon. At that time, I always heard at the breakfast table stories about Eros. Eros was coming very close to the Earth. That was in the year 1931, the close encounter of Eros, and everybody was excited about that. And the astronomers were all doing calculations to calculate the orbit and find out how close it would come. And so I decided to write a book about that, and it was called the Sir Philip Roberts Aero-Lunar Collision. And Sir Philip Roberts was an astronomer, and what I find remarkable is that I understood at the age of 8 that what astronomers do is not to look at the sky, but what astronomers do is to sit and make calculations. And that was what Sir Philip Roberts was doing. He made calculations of the orbit and predicted the collision of Eros and the moon. And so then the spacecraft was built to intercept the moon at the appropriate time to observe the collision. But unfortunately, the steam ran out of the engine at that point, so the novel remained unfinished.
Well, there's still plenty of time.
Yes.
And I can refer you to some asteroid people who refined the calculations for you. But as a teenager during the Blitz, did you find this a very formative or, shall we say, diverting period?
Yes, and I think, this is, of course, politically very incorrect, but I enjoyed the Blitz, and I remember so vividly lying in bed, listening to the bombs coming down from the sky, and then this delicious crunch of the buildings collapsing after the bomb went off. It was just so, it fulfilled all my hopes. I was, of course, a teenage rebel who considered the British Empire was an evil institution, and I could hear the empire just audibly crumbling. It was a blissful experience, and I think one should bear that in mind when thinking about events today, that for teenagers, death and destruction are not something to be feared, they're to be enjoyed. And that's the way teenagers are, and so it's quite, to me at least, it was very illuminating to look back and see how the Blitz actually looked at the time to a teenager. I don't remember ever being scared, but I remember being extremely happy.
Oh.
Freeman, did you share that with your parents at the time?
No.
Okay.
Well, it might have been even more exciting to go on fire watch.
Yes, so of course, there were other people who were far less lucky than I was, who came to grief, but that wasn't in my mind at all.
Well, it's said that we recapitulate evolution, and perhaps it's reassuring to know that Freeman Dyson spent time as a barbarian.
I certainly was, and I think it's quite clear we're designed that way, that as teenagers we take stupid risks, we are cruel and thoughtless, because that's the way we survived, and we're living in a jungle. That was the appropriate response. It's not so appropriate today.
So, Adam, you had questions about formation of Freeman Dyson, the scientist.
So this is a large jump from Freeman Dyson, the can't wait for the bombs to hit the buildings, to how you got involved in mathematical physics and quantum physics in particular, and how you connected with Feynman and really connected with quantum mechanics. So what was that jump from the Blitz to quantum mechanics?
So, well, of course, they all went on at the same time, but no, I had two gifts which were clear from the beginning, that I enjoyed calculating and I enjoyed writing. And so those are the two skills which have kept me going all these years. And so already as a child, I just loved numbers and I loved calculating. And
well, you wrote a story about a calculator, a person calculating. So it sounds like that was early on.
Yes,
Yeah.
and so the calculating numbers was what I did, and so I got into number theory quite early, and fell in love with it. And of course, I read this marvelous book, Men of Mathematics, by E.T. Bell, who was a professor at Caltech, and
a science fiction author.
a very good science fiction author. And so this book, Men of Mathematics, unfortunately, well, there's only one half of a chapter devoted to a woman mathematician. But apart from that, it's a very good survey of what mathematicians are really like. And it gave you this wonderful picture of the great mathematicians all the way back to Pythagoras. And they're human beings. They're people mostly quite flawed and people with ambitions and unpleasant personalities. So people, they were really human beings, and if they could do mathematics, why shouldn't you? And so this book actually caused many of the young people of my generation to become mathematicians. It certainly fired me with the ambition. If some lunatic like George Boole could do it, then I should certainly do it too. And anyway, so I became a pure mathematician and studied number theory and started my life that way until Hiroshima. And then after Hiroshima, I had the feeling, well, maybe that's something important that one should pay attention to, and that my skills could be used for doing something real in the real world rather than just theory of numbers. And so I had the feeling, well, I'd like to do something important, and number theory wasn't going to be that important, so I might as well go into physics. So it was, I think it was again the bomb that pushed me into physics. And then I thought it would be nice to get to know the people who built the bomb. And that led me to Cornell University, and where most of them were, and Hans Bethe and Richard Feynman, of course, in particular, and Philip Morrison. All three were leading lights in Los Alamos. So I found them right there, all three of them at Cornell, and got to be friends with them. And so my way to physics was, in a way, tainted with bombs right from the beginning.
So your collaboration with, to some degree, with Feynman, having to do with quantum electrodynamics?
Well, I never collaborated with Feynman. I learned everything from Feynman. He was professor, I was a student. And so I just listened to him talk, and it was, of course, I understood at once that he was a genius. And I mean, it was amazing luck. I arrived in America, and within 1 week, I'd never heard of Richard Feynman. Within 1 week of arriving in America, I actually became Richard Feynman's student, just by chance. I mean, it was just pure luck.
And Feynman didn't take students
No.
very often, so this is...
I attached myself to him, and it was perfectly clear he was the guy who I'd really come to America to get to know. And
so you worked with Feynman, and one of the things that you really popularized, I'd say first with the physicists, and of course maybe now more popularly, is the use of Feynman diagrams that weren't really being used by the physicists.
Well, I would say that's a gross exaggeration.
Okay.
I mean, Feynman was already using Feynman diagrams.
Fair enough. There was
and
one, yes.
lots of people knew about that already. All I did was essentially to explain why it all worked. So I translated Feynman into old-fashioned mathematics, which I knew, and so made it respectable. But all the ideas were there in Feynman. And of course, the fact that Feynman diagrams are also an art form was just a gift which came again from Feynman, not from me.
But don't you feel that mathematics and physics often lend themselves to beautiful art?
Sometimes, yes. It is. I would say one shouldn't overdo that. There's an awful lot of rubbish talked about art and science. But
Well, X-ray crystallography, for example.
well, of course, there are many examples. I mean, it is just a miracle that somehow or other nature speaks this language of mathematics, which we can understand.
Well, I won't disagree. Indeed. Well, let's go to the heady days of the 1960s. Those of you too young to remember them, you wouldn't have survived. But we did have pretty good music. And another thing we had was pretty darn boundless notions of the possible. Like how about taking a city, self-contained, like the Empire State Building, and landing it on Mars. I believe that you were part of that amazing era when all such things seemed possible.
So I would not quite say that, but we certainly had dreams of going into space with large spaceships, and we were going to zoom around the solar system exploring in the same sort of way as Darwin went with the Beagle to South America. And so we would land on Mars and stomp around and notebook in hand, observing everything on the planet. And then 5 years later, we'd come back to Earth and tell everybody what we found. But that wasn't quite the same thing. It was, we were not in the business of transplanting cities.
But a ship the size of a city.
No, our ships were not that size. They were the size of fair-sized ocean liner, but that's...
I meant a compact city. Of course, the method by which these things would be propelled might be considered politically incorrect today.
Yes, indeed.
We're talking about something called Project Orion.
Yes, which was done here in San Diego.
At General Atomic.
Right.
And your son actually wrote a very interesting book about you and the interesting people who you worked with in that era, right?
Correct. In fact, he knows much more about the history of it than I do, since he actually went back to the sources.
And what is the title of George's book?
It's called Project Orion.
And it basically, if any of you saw the TV series Ascension a while ago, it's based on that same premise, a very large, shall we say town-sized spaceship being propelled forward by atomic bombs. And I consulted for that show, referring to Freeman quite liberally. But the notion was that what if they actually had launched it in the 1960s? What would they be like now, after all these years? Do you ever have a wistful feeling about Project Orion?
Yes, of course we had. For me, it was a great adventure, and it was sad that we never got the green light. I would have loved to actually go into space at that time. But no, anyway, history passed it by. And I don't think it did have much of a future in any case. I mean, it had two fatal flaws. One was that it spread radioactivity all over the planet, which was a very good reason not to do it. And the second fatal flaw was that it was all secret, so you couldn't even talk about it.
And of course, it would use up our atom bombs pretty quick.
That was, of course, a great virtue. I mean, that was one of the that was one of the main reasons why I liked it, because it would go into space but also get rid of bombs. And
so you were a little bit different than the teenager.
Yes.
Yes. Well, the question then is, do you think that Orion might be resurrected with pellet containment, inertial confinement fusion?
No, absolutely not. I mean, this whole idea of carrying the fuel with you is not a good idea. It's just far too, the apparatus for propelling pellets or anything else is much too massive. So I don't think that kind of a system makes sense, and it wouldn't either today or in the future. What you will have in the future, I'm sure, will be public highways, which are essentially just pure energy, laser beams or microwave beams. And your little spacecraft is then quite small and does not carry the fuel. The fuel is in the beam and not in the spacecraft.
So imagine a industrial facility, a great big industrial facility orbiting the moon, taking in sunlight, and then shooting either microwaves or lasers at a sail and accelerating that sail and the small spacecraft, sports car spacecraft, all the way to Mars or wherever.
Yes, it doesn't need to be a sail. It could be any kind of a collector that can collect the energy. It's only a sail if you want to go really fast.
All right. Adam?
So going through the 60s, you've worked on now space travel, you've worked in physics, you've also started to think about climate change a little bit in the 1970s with this secret organization that we all know about, Jason. Tell us a little bit about your work on climate change, but also how you start to broaden. Is there a common thread of calculation and mathematics through this process?
No.
No, okay.
No, I mean, I had the midlife crisis like other...
Midlife crisis, you went right to climate change.
Especially, no, but especially theoretical physicists have this problem that we don't do well after the age of 40. And
oh, that's sad.
The time.
Okay. Thanks for telling me.
So generally speaking, with a few exceptions, of course, we have this problem which comes up at about the age of 40, where we're not competing with the brilliant young people anymore. So you have to find another line of work. And so that's not difficult. If you happen to be a gifted teacher, that's fine, or you go into administration, or you go into any kind of public service, maybe even become a politician. And my choice was to become a writer, because a writer was my skill, which was there in addition to mathematics. So roughly at the midlife crisis, which occurs in my case, I think it was age 42, anyway, I made the decision that from that time on, my main job was writing books with science as a hobby. And when I'm writing, of course, my interests are much broader than my skills, so that I could write about a whole range of subjects in which I had no skill whatever. Amongst them, of course, all these art and biology and history and all the parts of culture which are in many ways more interesting than science. So from that time on, I was free to expand. And I was, of course, as a result of the wartime experiences, I was all the time, of course, worrying about war and peace. So most of my books actually are more about war and peace than they are about science. So the problem of nuclear weapons, nuclear war, other kinds of war and peace have been central to my thinking and still are.
So, yeah, I'd like to extend this to the opposite end of time. And then we'll come back and talk about war and peace and climate change. But I'll tell you, one of the reasons why I so wanted to meet you back in the 80s and 90s was because of, I don't think there might have been a dozen people on this planet who posed it this way. But I believe you will be looked back on as one of the two physicists competing for a rare title and that is the greatest theologian of the 20th century. And the reason is very simple. A fellow by the name of Frank Tipler wrote a book called The Physics of Immortality, which is probably one of the greatest science fiction novels ever written. Pardon me. Bizarre, brilliant, weird. But his notion was what would be the eschatology and the essentially long-range theology of what if the universe kept expanding until gravitation slowed it down, and then it fell back together into the great crunch. And he posited that in the last million years, all the beings that had been separated by the speed of light would be able to communicate, share their wisdom, and in the last million years, become essentially godlike. You wrote fascinating eschatologies about what if the other is going to happen. What if the universe keeps spreading and spreading and spreading and spreading until the stars become invisible to each other, the last red dwarfs fade away, they become too cool even to exist. Yeah. And so beyond that, is there a way for life to continue? And you wrote about this, and at the time it struck me, these two fellows are talking the most important long-range theological questions, and the universe will decide which one is right. And the universe chose Freeman Dyson.
No, absolutely not.
Oh, there I go again.
Yeah, no, of course, that's the big joke, that nature always has more imagination than we do. And so actually, it turns out that both Tipler and I were 100% wrong.
Weren't you less wrong?
No.
But wasn't your theology, your eschatology based upon the notion that things keep expanding?
That we keep expanding uniformly, and that was essential. And so that is totally wrong. Everything I calculated there was wrong, and just as wrong as Tipler.
Oh, he had this, you had this.
And both of them are wrong. The real universe...
Wrong is wrong.
The real universe, of course, is accelerating, as we now discovered just in the last 10 years. And that changes everything. So that, in fact, neither of our models makes any sense in the light of what we now know.
There is a rambunctiously honest fellow. I gave him a perfectly fine excuse because he is not equally wrong with Frank Tipler. It is expanding. But notice, he has absolutely no need to preen.
No, in fact, the fact that the universe is accelerating, of course,
yes,
is enormously interesting because it's totally unexpected, totally mysterious. It's one of the really important problems that we don't understand. And the theologians are always 100 years behind, and we still are.
I still think that you were the winner of that contest.
So
so far there's no winner, and I hope there won't be. I think, in fact, the great thing about science is it's all about things we don't understand. That's what makes it so exciting. And because the public propaganda is just the opposite. It's public propaganda always says science is things we know, but it's just the opposite.
And the wider we expand our territory of what we know, the bigger the perimeter is.
Right. That's the beauty of it.
So Freeman, this cosmic expansion, dark energy is one of the surprises. What other surprises have emerged in cosmology that you never would have anticipated?
Well, there's also dark matter, which of course was discovered by Fritz Zwicky here in California, and nobody believed him for about 50 years, but he was right, and he actually saw dark matter quite clearly for its gravitational effects. but he was a cantankerous individual, and he was a physicist, and the astronomers thought they couldn't allow a physicist to prove them wrong, so they didn't listen to him.
Oh, fellow Caltecher.
Right, but he was in a separate building, and the astronomers didn't communicate with him. And
I featured Fritz Zwicky in my first novel.
oh, good.
Yes, amazing character.
So another large question you've discussed a lot, particularly in the last several years, is this question of life in the universe as well.
Yes.
And of course, that was something that Arthur C. Clarke was also very involved in his work.
Yes, and that's, of course, another big mystery. We started searching for life in the universe with Frank Drake in 1960 or thereabouts, and so we've been doing that now for 55 years. We haven't heard a whisper, and that's a big disappointment, and we still don't understand why.
Yes, there's some fascinating questions, and I've spent 40 years cataloging possible explanations for what's sometimes called the Fermi paradox. Of Enrico Fermi asked, "So, where are they?" And it's a very interesting question. And among the questions is that they're listening to us puzzle over it right now and chortling over the fact that we're still bemused and that we suspect we're being listened to but can't prove a thing.
We talk a lot about very Earth-centric type of life, the kind of life that we see around us, because of course we have the one experiment that's been successful so far. But you've also talked about very different forms of life that would exist on much longer time scales out in the outer Kuiper Belt region. What other forms of life do you imagine that we are missing because we don't know how to look for them?
Well, I always say you should look for anything that you don't understand, and that should be the criterion. Don't try to imagine beforehand what life is going to be like. Life is something we just cannot imagine what form or shape it might assume. So I think it's a mistake to program searching for life as a separate enterprise. It should be just a part of exploring the universe. When you find something you can't understand, then maybe that's a sign of something living. Almost certainly not. I mean, a good example of that, of course, is these things which are mistakenly called Dyson Spheres, which should be called Stapleton Spheres. It was actually Ola Stapleton, the science fiction writer, who had this idea, which I stole from him unintentionally. Well, so my name got wrongly associated with that. But a Stapleton sphere is an artificial construction using the energy of a star, which Stapleton described in his novel, The Star Maker. And those objects, of course, turn out, when we started looking for them, which was the first infrared satellite, IRAS, the infrared astronomy satellite, was looking for such objects in the sky. And of course the joke was that we found millions of them. Turns out nature is absolutely generous with these objects, and every star starts its life with a big dust cloud around it. So it looks just like one of these spheres, and there's no way to tell the difference. So the search failed, not because we didn't find them, but because we found too many.
And they were natural.
Well, presumably they're natural.
Either that or we got a lot of neighbors. But it's the cool stars.
Yes,
it's
absolutely.
the cool stars.
It's always cool stars.
Well, actually, while we're on this business of life, and of course there's another name, Kardashev, which comes in because a Type 2 Kardashev civilization would enclose its star and use up all the energy from the star. But one of the things that shows how wild and imaginative your mind really still is your notions about vascular plants. And I have a story recently, and I'm going to be giving you this. It's hot off the press. You get copy number 1 of my new short story collection.
Wow, thank you.
But there's a, just arrived. But the story in there is that the solar system blooms with life because we seed it with these life forms that can dig roots into asteroids or into the bottoms of Europa-like oceans, and then have a vascular-like trunk that gets up through the surface and then collects the solar energy out at the surface. And I was so impressed when we talked about that at the Starship conference that we had here. Would you like to elaborate a little bit more about that insight?
Yes, well, I call these things warm-blooded plants. The fact is that most of the real estate in the universe is cold. I mean, real estate means surface area where things can grow. But most of it, in fact, is small objects, comets and asteroids and snowballs floating in space. There are billions and billions and billions just attached to the sun, and presumably all through the galaxy. So if you calculate surface area rather than mass, this is the most abundant part of the universe. So the question is, why are not things living there? And the reason, of course, is that it's cold and it's hard to get started. But if you had a warm-blooded plant, like a polar bear on this planet, it could live and flourish under those conditions. And on this planet, for some reason which we don't yet understand, animals learned how to do that. Polar bears are living happily in the Arctic. Penguins are living happily in the Antarctic. But there are no warm-blooded plants. That's why there are no plants in Antarctica. Why not? I don't know. But anyway, so that's the concept, that you could imagine a plant which grows a kind of greenhouse around itself. So it has a transparent structure built out of organic materials, a transparent shell. Inside it's warm, outside it's cold. And such a structure could exist on the surface of these cold objects anywhere within range of a sun or a star. And it could keep itself warm and then provide a home for any kinds of other creatures which could take shelter among its roots. And the roots would then go down, as you describe, into the ice and collect nutrients. So it would be living on the surface, which is cold and with no atmosphere. But the great advantage of this form of life, once it gets established, is it's easy to escape from that kind of a body. The escape velocity is only a few meters per second or even less. So it could easily jump from one place to another. So once life got started in that environment, it could actually spread all over the galaxy.
But you're right that getting bootstrapped to this fairly complicated kind of organism that has no natural way to get started, that this would likely come about as an act of creation by intelligent life.
Absolutely. And so I like to think within 20 years we will have roughly sequenced the whole biosphere of this planet. As we've sequenced about 20,000 species already, and the total number of species is about 20 million. And at the rate things are increasing in speed and cheapness, we'll have the whole biosphere sequenced in about 20 years from now. So you could imagine then a thing which I like to call a Noah's Ark egg, which is an object the size of an ostrich egg with weighing a few kilograms, containing the genomes for 20 million species. And you just throw that out into space, and if it lands in a suitable environment, it can grow into a complete biosphere. So you're not just seeding one plant, you're seeding a whole biosphere which could be self-sustaining and then continue to evolve. So in that way, we could be spreading life through the universe very cheaply.
Shall we pity this fellow for the crisis he experienced of declining creativity at age 42? I think you managed to find some ways to keep that wild mind going. And of course, as a fan of your son and daughter, who are dear friends also, I would like to, I think that it may be time to open. Are you intimidated yet? Well, if you haven't thought of any questions, think of some, but let's see who's the bravest among you, or I'll follow up with, I'll have the temerity and courage to ask this rascal.
We have two microphones down here.
About climate change. So you're going to have to rescue, otherwise I'm going to ask him. Yes.
Freeman, could you say a few words about birds and frogs?
Do you want me to repeat the question?
Yes,
Birds and frogs.
Yes, that's just a convenient way of describing scientists. That they're the kind who fly high and look down from a distance at all kinds of problems all the way to the horizon. So they're looking at the big picture. They're cosmologists and what they call systems biologists, people who look at the structure of things on a large scale. And then there are the frogs who live in the mud below and examine particular objects and study small problems much more deeply. And so I have the pleasure myself of being a frog. Some of my friends are birds. It takes both kinds to do science.
I would say that most people in this room doubt your inability to fly. Yes.
Thank you. I've actually got two questions. The first is very important to me personally. At the age of 71, I'd really like to know what you've been eating and drinking.
Well, we'll ask the better looking and by far smarter member of the Dyson.
Oh, that's the problem. The second question, though, is that, speaking of mathematically inspired physics, did you have a personal reaction to the actual measurement of a gravitational wave in October?
Oh, yes. I mean, that's wonderful. I mean, of course, the beauty of it is that we discovered real black holes of a size that we know should exist, but we've never seen. And so it wasn't so much that the gravitational...
That's the sound of black holes.
Yeah, it sounded just like that. It's amazing.
It was a chirp.
Yeah,
That was the chirp.
Yeah.
No, anyhow, I mean, this is a marvelous discovery. And of course, I mean, the beauty of it is not just that particular object, but that we now will see many, many more. This is a new window into the universe. We shall see many gravitational processes which we have only conjectures to describe.
It's fascinating to me how many different things come from collisions. The fast radio bursters, they now believe, come from the merging of neutron stars. And as we get more sensitive instrumentalities, then we'll be able to merge the continua of this. And what strikes me most about this LIGO result of the gravitational wave is that we're talking about something that happened, 1.4 billion years ago, and yet seems to happen often enough that we would encounter such a thing over the lifespan of such a project, and that we'll very likely
Catch a lot more.
Catch others.
Yeah.
Does this give you any inkling how big the universe is? I mean, it's the biggest thing out there. I mean, it's really, really big.
So I see a young fellow there. Let's give him a chance.
Have you met Einstein personally, and what was it like?
Unfortunately, I never spoke a word with Einstein, although I saw him very frequently. But it was he was an old and very distinguished gentleman, and he was very occupied with the affairs of the world. He was doing a great job as a politician as well as a scientist. So I didn't want to go and bother him, and he was much too busy to bother me. So we never actually got to know each other.
I'm told that I saw him play the violin when I was 3. That's bragging rights.
Good.
Oh, did you have a follow-up?
No.
Well, then we expect you to follow up creatively across the next 80 years. All right?
My question would be if you have a suggestion, like an alternative to Tipler's omega point, and if that might include the formation of a bubble universe by construction of negative energy around a positive energy density, or to form a bubble universe or something. What alternative would you suggest to that in order to preserve life or to expand its influence in anywhere from a physical to a metaphysical sense at the end of the universe?
Well, that's not a question I've ever considered, so I don't have anything useful to say, I'm afraid.
Though he did talk in one of his books about how baryonic matter might be able to continue in some degree of intelligence after the end of the stars, after the stars burn out.
Well, that's in a uniformly expanding universe.
Oh, okay. It would be at least somewhat applicable in an accelerating universe. But the interesting things that are happening in our sense of the size and scale of what one might call a universe in the last 25 years have been amazing. When I was a forming embryonic physicist, all the stodgy, cosmologists said the Big Bang is all there is. And it's not an explosion, it is an expansion of metric, completely isolated. Sometime in the last 20 years, it's become an explosion again. An explosion inside something much, much vaster. Now, this is mind-boggling, especially when you were taught the catechism that it's not an explosion, that it's isolated, it is its own thing all by itself. And the fact that we live that the high priests of this era are comfortable with such a transition is somehow comforting to me. I don't know about you, Freeman. Did I describe it at all?
No, I must confess that to me doesn't resonate at all. I mean, I have a sort of strict construction view of science. Science is about things we can measure and observe, and anything outside that is literature. Literature is great. It has its own standards, it has its own value, but should not be confused with science.
And so you would classify string theory under literature?
Not necessarily. That remains to be seen. But I would classify the multiverse as literature. There's something that goes outside the universe.
Do you think there might be experimental ways to tell if it's an explosion into something or if it's just a self-contained?
Of course, I mean, there's a whole lots of things we haven't yet observed. Also, I'm not at all surprised if there are all sorts of interesting stuff out there. But I find that sort of making pictures of it in our present state of ignorance is not science.
All right. Adam, did you want to follow up?
I did want to comment that Sir Clarke, and I'm going to get the quote wrong, but he questioned intelligent life's survival value. So we may not need a survivability of intelligent life. That may just be where we end up.
Adam, where do you lean?
I'm a little pessimist.
Where do you lean on this whole question of whether or not there might be multiverses?
I would agree that this is, at this point, still a nice story.
And we have a video on multiverses from an event that happened. that happened here at UCSD's Arthur Clarke Center. The Clarke Center also was graced by Freeman at an earlier event called the 100-Year Starship event. And so you are
free to watch and make your own choice.
Look it up on the archives. And those of you who are not on the mailing list for the Arthur C. Clarke Center for Human Imagination, you can get online.
At the Starship Symposium, in my ignorance, I asked a question and called you Dr. Dyson. And I could tell it was a faux pas because about every head in the front two rows turned around and looked at me with some disdain. Unless in my own ignorance you don't like to talk about it, why is that in your own words?
What's the question?
Being a doctorate.
Are you going to go back now and get your doctorate?
Oh, no, please not. No, I hate the PhD system, and I've been fighting all my life unsuccessfully against it.
But you get to wear a neat cowl one day.
I wanted to ask briefly, you described your warm-blooded plants and hopping from asteroid to asteroid. Was this inspired by The Little Prince, or was there any connection?
Probably yes. I mean, certainly I love The Little Prince, and he had all the right ideas.
So just if I can ask a follow-up, what is your vision for what children in the future might be learning? What do you think is important for more Freeman-like people in the world?
Well, of course, my hope is that biotechnology will become the new art form that we have in the 20th century. The new art form was the cinema, which in a way was the dominant art form for the public during that century. And now we need a new one, and I hope it will be biotech, so children will fool around with genes and will compete who can produce the cutest dinosaur, and so that will be the talent which people have with flowers and with gardens should somehow be enormously enhanced when we can use scientific and technical means in addition to the old-fashioned means. So I hope that there will be a great rejuvenation of art through science in that combination. But of course, it has also its dark side, which doesn't need to be emphasized.
No zombie apocalypses.
So I actually want to follow up on the question. So we talked a little bit earlier about the process of science and how it's changed since you started in the 1940s and 50s to where we are now. Can you comment a little bit about what you see as not just the new ways of science is followed through, but sort of the process of science, how we make discoveries, and whether we are going to be able to have another Freeman Dyson in that process?
Oh, well, I mean, Freeman Dysons are cheap, and you can certainly, I think the main point is not to have science too centralized, and countries that centralize science usually don't do well, and the ones that do well are generally those that leave a lot to amateurs, and so I've always been pushing the role of the amateur, especially in astronomy, and it's very fortunate that in the last 20 years that the technology of mirrors and optical processing and data processing in general has got cheaper and cheaper, so that it is possible now for amateurs to have really good equipment, and a lot of amateur astronomers are actually doing pretty well, not quite on the professional level, but pretty close. And so I see that as very much a bright prospect for the future, and that we'll rely less on big organizations and more on small groups of enthusiasts. And I hope the same thing will happen in biotechnology, and that's why I think biotechnology as an art form should be one of the main advances in the next 50 years.
And I think it's important to mention that if any of you are enthralled by this concept, the Association of Amateur Scientists is a large and very thriving group, and many scientific communities, astronomers in particular, and biologists and naturalists, depend on their networks of amateurs who learn a lot and participate. Now that with the internet and all that, the participation is easier and more fluid than ever. And of course, now we're seeing things like what are called CubeSats, which are small satellites, that are ejected as parasitic cargo when we send out expensive satellites. And more of these things are deploying in orbit. And it's reached the point where they're going to be deploying their own solar sails and going on planetary missions. And small groups of people are making those.
Yes, this is just something I'm very happy about.
I'm keeping score of the number of times I've been rebuked and praised. Tom, did you have something?
Yeah, first of all, I want to thank Sheldon and the group here at the foundation. It's just an incredible way to spend an evening, and makes you proud to be a member of a civilization. But anyway, I didn't hear anything about climate change, and I know you have an opinion on this, and I'm happy to hear it expressed. But jumping ahead to the amateur science and astronomer thing, which I agree with very much, so I'm a very active amateur scientist myself, is there a position for climate change understanding and adaptation in the amateur scientist? Are there opportunities for sensing and adaptive control technologies that are very small scale, large scale, small items and things like that, but the massive network effects of citizens working together? Can you speculate on any ideas we might have for understanding our climate that way?
Yeah, well, I'm not an expert on climate. I never pretended to be. I'd like to correct the statement that I'd worked on climate with Jason's. Actually, I worked at Oak Ridge National Laboratory, which had an excellent group doing climate studies in the 1960s and 70s, led by Alvin Weinberg, who happened to be a physicist. Anyhow, but they were particularly interested in the natural interactions of climate with the ecological aspects, with soil and vegetation as part of the climate system. So it had a much broader concept of climate than other parts of the community. So that's why I like to go to Oak Ridge. And I think the conclusions we came to were still, I think, valid, that climate is far more complicated than most of the experts believe. And that's still true. The experts sort of consider it a problem in fluid dynamics. They have these beautiful models which represent fluid dynamics, but nothing else, which is only a very small part of climate.
I should mention that, in some of the defense work that I'm engaged in, there's a lot of discussion of what's going to happen to these, our cell phones. And we are just now getting into the new era of cell phone sensors. The first was the camera, of course. And now you have these little these little card readers, credit card readers that let you do commerce anywhere. But they are becoming sensitive to infrared. And as time goes on, they're going to be taking on more and more of the capabilities that Eric Viry is studying here as the Clarke Center's medical director, studying the tricorder X Prize to develop Bones McCoy's X Prize, a tricorder for studying human ailments. And as these sensors proliferate into our phones, this whole business of confronting the police with cameras, for example, is just the beginning. You're going to be detecting pollution. You're going to be part of a network of 1 million fellow citizens who are collecting data. You ask about how amateurs could deal with climate change. I'd love to see an amateur network simply, absolutely verify ocean acidification, separately from and independently of all the professional scientists. If that were to happen, I think it would have substantial political effects, because this is something that cannot be denied. Can we make room for some others? Yes.
So, given our current technology, we find it a lot easier to send out robots and satellites into the solar system. So what do you think the probability is that instead of encountering biological life forms first, we might encounter robotic emissaries from other civilizations?
Well, it's very high. I would say if anybody was looking for human activities, they would probably notice spacecraft flying around the solar system today. And so it's very likely that would be the case. But of course, it depends entirely on their local habits, which we don't know about.
Yes, the notion of what are called von Neumann self-replicating probes or interstellar probes. Clearly, if humans go to the stars, at least most of the first few waves will be robots who think of themselves as human and call themselves human because we asked them to. But the notion, I think, is very important that we recognize one thing, and that is that 2015 was by far humanity's best year in space. Vastly, vastly better than the Apollo era. And it is a sign of the horrible mood that this nation is in, that we would accomplish a year like 2015 was and not even notice it. Yes.
I wanted to know who your heroes were and why.
So can you repeat the question?
Yeah.
Son?
I want to know who your heroes are and why they're your heroes.
Oh, my heroes. Well, I would say Matthew Messelson, perhaps number one. He was a biologist who is still around, a very excellent biologist, who is personally responsible for getting rid of biological weapons. That was an amazing achievement. I mean, of course, when I say getting rid, I mean legally. Biological weapons are illegal all over the world, and it doesn't mean they don't exist, but they have to be hidden and they can't be used politically. So that is, I think, an enormous achievement. It was sort of the biggest act of really getting rid of weapons that we have seen. And Matthew Messelson happened to do it because he was a friend of Henry Kissinger, and Henry Kissinger was in a position to do it because he was a national security advisor to President Nixon, and President Nixon was in position to do it because he was a right-wing Republican. And you have to have all three in order to get it done.
Yes.
In light of your comment that at age 42 you wanted to shift from being a scientist first to being a writer first, I wanted to ask, in your now majority of your life as primarily a writer, could you share with us a favorite novel, a favorite play, or a favorite poem?
Yeah, it takes too long to think of all the plays and poets. But I mean, let's say my favorite poet is William Blake,
Yes.
and
Jacob Bronowski also adored him.
yes, and the Marriage of Heaven and Hell is perhaps my favorite poem. It's not much. I mean, it's mostly prose rather than poetry. But anyway, it's a great piece of writing.
Yeah, my question is, what is your take on it from bit and the role of information theory in physics?
So what again? I'm sorry, I'm not hearing that well.
What is your take on the slogan "it from bit" and the role of information theory in physics?
Yes. Well, that's poetry, not science, and it was. I mean, John Wheeler, of course, was the author of that phrase, and he was a poet as well as a scientist. But I think, and he was aware of the difference.
Hi, David. My question is, our civilization uses a tremendous amount of energy. And your writing, you talk about the Dyson sphere where you could gather all of the energy of a sun. What do you think, or have you thought of, or what does your imagination tell you that we might do with the energy of a sun that we don't do now?
Yeah, well, that's of course a big question with many aspects. I'd like just to say what we could be doing right now with biotechnology, that we don't yet quite have the science, but it will come along in the next 50 years or so, that we could imagine forests which don't ever need to be harvested. That would make a huge difference. That you grow trees, the trees produce liquid fuel. Liquid fuel is fed down into the roots of the trees in living pipelines underground and collected so that we have a perpetual supply of liquid fuel. The trees stay alive and they are not chopped down. And they can be, of course, a beautiful forest of many different kinds of species of trees with wildlife and all the beauty of a natural forest, and producing energy in a useful form continuously from sunlight. So that's something we could do right now. And I think to a great extent it would be a solution to the energy problem, because the amount of sunlight that falls on the planet is about 10,000 times as much as we are using. So we don't need to cover the whole planet with forests. It would be enough to have a few % of the planet covered, and that would, if you could make the trees so that they don't need to be chopped down, the environmental aspects would be totally different and much more, to my mind, much more attractive. And of course, it doesn't only apply to trees, it would apply to all kinds of crops. They could be grown without being harvested, and so they could also accommodate natural species of all kinds of animals as well.
Yeah, I took this idea of yours one step farther, and they're deciduous. And so when they drop their leaves happen to be solar collectors and are that year's crop to go on our roofs. So, I mean, why not?
Absolutely. No, that's a good idea.
Thank you very much.
Go on, Adam.
I'll stay on that topic. I really did want to ask some physics-related questions, but it seems to me with regard to harvesting energy off the sun and making it useful in the biosphere, that one of the main, we have sort of high-efficiency solar collectors, right? 10%, 20%, much more efficient than your typical leaves can produce. But what is key, it seems to be, is this energy storage problem. It's not just producing electricity, but doing something with it, and hopefully, storing it up so you can use it at nighttime. Any thoughts on Sadoway over at MIT and his inventions of energy storage? Or is that a key problem in your mind?
Well, the simple answer is, of course, liquid fuels. That's why I have these trees producing liquid fuels, just precisely for that reason. That's the way of producing energy which is easily stored. And but of course, things that there are many other interesting projects which this MIT project I don't know about, but certainly there are many groups of people doing very useful.
He's doing grid level storage, so it's typically high temperature. Sort of in a sense like reversing the thing with aluminum. Having anyway, Sadoway is worth
also
looking up.
Compressed air, and there's raising water up.
Those require,
But certainly liquid fuels are far more convenient and far easy to move around from one place to another.
I think we should just take a couple more. I guess it's been a wonderful evening, but yes, sir.
Thank you. Richard Feynman, in his lectures on the nature of physical laws, commented that physical laws ultimately cannot be explained apart from the mathematical equations that are used to characterize them. You know, in other words, an atom is really not adequately described as a small, you know, like a small satellite with, or a small body with satellites, or even a cloud or whatever, electron. Can you comment on the challenges of translating science to literature and making real fundamental laws of science and physics accessible to a wider audience? Just, it seems to me, it virtually requires, you know, commonplace explanations, but they clearly have limitations. Can you talk about that trade-off?
I don't think I have anything new to say about that. I mean, the amazing thing is that science if you look at theoretical physics, which is my own field, that it's all about complex numbers, that nature somehow or other speaks complex numbers, not real numbers. That's something that, to me, is a total miracle. I mean, we invented complex numbers which appear to be totally artificial. You add x plus iy, where x and y are real numbers, and that's a complex number. It seems to be a very artificial thing to do. But nature does that all the time. And that's why quantum mechanics works. And so that's the sort of basic reason that mathematics is so powerful for describing nature. But we still don't really understand why. And I think it's very hard to make that accessible to the general public. But the complex numbers is not something that ordinary people can easily grasp.
So our last question.
Yeah. Hey, so what are your thoughts on virtual reality?
On virtual reality?
On virtual reality, yeah.
Well, I mean, I admire it from a distance. I have nothing much to do with it, but clearly it's wonderful what you can do. The finest example of virtual reality that I remember was a conference in honor of Arthur Clarke that was held in Telluride. I don't know whether any of you know, whether any of you were there. Telluride is a town in Colorado where it happens that Neil Armstrong lived there when he was alive. And anyway, they had a conference in honor of Arthur Clarke. Arthur Clarke was in Sri Lanka and couldn't travel. So we had Arthur Clarke holographed all the way from Sri Lanka to Telluride. And there he was in 3D, and he talked to us. And he was absolutely alive, 100% Arthur Clarke. There he was, the total hologram. You could see him from all sides. And he could only see one at a time. He could only look in one direction. So we took turns standing in front of Sir Arthur and having conversations. So anyway, that was the finest hologram, the finest virtual reality I've ever seen.
And he managed to segue to Arthur C. Clarke.
Yes, we really. Well, I want to thank our great panel for such a wonderful evening, and thank our guest of honor, Freeman Dyson, for giving us a really inspired way to look at the universe. So thank you all. And come back.